very fun chapter. It covers resonance, and the goal of this chapter is we're going to look at resonance and how resonance affects the structure, bond length, and bond strength of organic molecules. And then we're going to look at effects of structure on function by looking at various case studies in acid-base chemistry. So with that established, let's start and get a sense of why do we need to consider resonance? Why do we need to be concerned with resonance's role in structure? Well, when we think a little bit about Lewis structures are often inadequate to describe the true structure of a molecule. So for example, if we look at the acetate anion, CH3CO2-. So if we're using our functional group approach, so reading from left to right, what's the first functional motif that we should draw? CH3, okay? And connected to that CH3 is what? Yep, carbon, okay. So I'm gonna draw a series of 2 lines to represent our 2 carbons, and then attached to this carbon, this CO2 group. So anytime you see the group CO2-, what is that a derivative of? What functional group derivative is that? Yep, exactly. So this is a derivative of a carboxylic acid, which is CO2H, which looks a little bit like this. So this is the deprotonated form of acetic acid. Now, when we look at this Lewis structure, it looks quite innocuous at first glance. However, let's try to entertain this question. If we have these 2 carbon-oxygen bonds, 1 and 2, let's try to answer the question, which carbon-oxygen bond is stronger? So let's give our first pass interpretation. Just using our principles from Chem 101, staring at this molecule, is there any difference in strength between these 2 bonds? So you think, which bond would you expect to be stronger? Bond 1. So our initial interpretation is I expect bond number 1 to be stronger. However, in reality, if we account for resonance effects, what we actually observe, if we look at the structure of acetate, what we see actually is that both carbon-oxygen bonds have the same length and strength. And the most interesting thing about this observation is not just the fact that both of these carbon-oxygen bonds have identical lengths and strengths, but it's due to the nature of these carbon-oxygen bonds. So the best way that I like to portray the carbon-oxygen bonds found in acetate is instead of being quite a single or double bond, they're best considered an intermediate strength between a single and double bond that we'll coin a 1.5 bond. So it's not quite as strong as a double bond, but it's much stronger than your typical single bond. So what are some takeaways from this? Our goal in this chapter is to try to rationalize, why do we observe this 1.5 bond in acetate? Why do we observe these irregularities in bond length and bond strength? And the key driver behind this is a phenomenon known as resonance, where our electron density found in our double bond is spread over multiple atoms, multiple conjugated atoms. Okay, so this is really my lead-in to help everyone just to be aware and to really appreciate the role that resonance can play in structure, bond length, strength, critical topics in organic chemistry. So let's try to rationalize and let's explain how do we draw resonance structures and how do we interpret resonance structures. Does that make sense so far? Okay. So, our Lewis structures cannot fully describe the actual structure of many compounds. So in resonance, resonance structures, we'll be drawing a lot of these in today's class. These are one or more valid Lewis structures with the same skeletal formula, but a different distribution of electrons in bonds and lone pairs. So for example, for acetate, we drew our first boilerplate structure that looked a little bit like this, right? So this is our first structure that we drew for acetate. Now, an example of a resonance structure for this molecule of acetate, the way to draw resonance structures and the way to signify that you are drawing a resonance structure is you first put your structure in brackets. You designate resonance by using a double-headed arrow. So this is your key that we are drawing resonance structures. Now, to show you an example of a resonance structure for acetate, instead of having the double bond between the topmost carbon-oxygen bond, instead we're going to have a double bond with the bottommost carbon-oxygen bond. So we have the same skeletal arrangement, correct? We have the same connectivity of atoms, but is there a change in how our electron density is distributed? Is there a change in how we have drawn our lone pair and double bond? Yes, so this is the principal idea of a resonance structure. Same skeletal connectivity, different arrangement or different drawn arrangement of electron density. Now, a critical point that we need to discuss when we talk about resonance structures is the actual distribution of electron density in the molecule, and the actual structure doesn't match any of these resonance structures. These are just our pictures to help us get a sense of where electron density can be distributed in our molecule. In reality, none of these pictures are an accurate descriptor of the actual bond length and the actual bond strength. Instead, the actual structure is best thought of as a weighted average of all resonance structures based on their favorability and overall stability. So these two structures are not just interconverting. They're not interconverting. These are just pictures for us to get a sense of how can electron density be distributed. In reality, the actual structure of our molecule is somewhere in between these resonance structures. Okay? So we are yes.
So you took in the resonance structure itself.
Yes.
That line is that not signifying the double bond? It's just signifying that they kind of sharing it.
Which one?
It's like the double bond. It's not double bond.
Oh, so these are both. I've drawn them both as formal double bonds. So the source of the 1.5 bond that we discussed earlier is what's known as a resonance hybrid, where we take each of these resonance structures and average them together. Does that make sense? So in the structure on the left, we have a double bond between the topmost oxygen and our carbon. In the rightmost structure, we have a double bond between the bottom oxygen and our carbon. Mm-hmm. Yes.
So basically what happened between those two is you switch the two hydrogens and their bonds to put it on different.
I switched what?
Like those two oxygens, so we have different electron pairs. And
yes.
Switch them to.
Yes. So we changed the location of our double bond from the topmost oxygen to the bottommost oxygen, and we'll talk about the logic behind how to draw resonance structures in a moment. Yeah. So. A key feature of this idea is the actual structure we observe is a weighted average of all resonance structures. So what we're next going to do is we're going to talk about the criteria that we use to assess whether a resonance structure is major or minor. So what makes a resonance structure favorable? Well, in general, just like Lewis structures, favorable resonance structures will minimize formal charges, will satisfy the octet rule, place negative formal charges on electronegative atoms and positive formal charges on less electronegative atoms. And in general, opposite charges should be placed on adjacent atoms if ideally. So these rules are ranked in order of importance, just like with Lewis structures, right? What was our overall goal when drawing Lewis structures? So what was the first thing that we always focused on? Formal charges, and then right behind that is the octet rule. The reason why I have it in this order is that some atoms do not typically follow the octet rule, and the formal charges typically win out in many examples. Now, to really help showcase this idea, I really want to emphasize that resonance is not rotation of a molecule. So we're not just rotating our view of a molecule. It is a change in the distribution of electron density, or our drawn distribution of electron density. Okay, so let me number these carbons. 1, 2, 3. So this is a classic system that's often studied when looking at resonance. So we have an allylic cation. So a cation, a positively charged carbon, adjacent to an alkene or a double bond or a pi system, however you want to call it. Now, a common mistake I often see students make is that they just rotate the molecule around and say, oh, wow, I've drawn a resonance structure. If you have not changed the distribution of electron density between your atoms, you are not drawing a resonance structure. Notice how these two structures, is the positive charge still on carbon 3? Yes. So make sure you don't fall into the habit of just rotating your molecule. Resonance is not rotation. An example of a resonance structure, and to showcase I'm drawing a resonance structure, I'm going to use these double-headed arrows. I'm going to move my electron density from my double bond to the carbon to share my electron density between carbon 2 and 3. We often draw resonance structures using arrow pushing notation, which we'll talk about in a moment. So an example resonance structure would look something like this, where now if we number our carbons, have we moved the location of our double bond to be between two different carbons now? Has our double bond shifted in position? Yes. So does everyone get the distinction between rotation versus a resonance structure? Yes.
So you drew it flipped around. Can you
Yes.
also draw that same thing, but just flipped the other way?
Yes, exactly, exactly. The reason why I drew it flipped is just to show, in this first case, we've just rotated. We've drawn the same molecule. These two molecules are exactly the same. In the second example, I've changed the distribution of electron density that I've drawn. Now there's a double bond between carbon 2 and 3. So as a result, we're now drawing a resonance structure. Same skeleton, different arrangement of electron density. Does that make sense? Okay. So what we're now going to do is we're going to take a look at resonance structures and get a sense of the actual molecular structure. So as we've discussed, the actual structure that we observe is a weighted average of all resonance structures based on their contributions, okay? So let's take a look at some resonance structures and let's get a sense of whether we can label certain resonance structures as major or minor. That's your goal in this chapter, to get a sense of which resonance structures are major or minor. So when you're trying to show the movement of electron density, trying to show how you have redistributed electron density to get a new resonance structure, there are two major methods. The first of which is known as the curved arrow method, where let's suppose we're going from resonance structure number 1 to resonance structure number 2. Now, in order to accomplish this, what needs to happen? So first and foremost, let's think, where are we putting electron density? What atoms are we putting electron density? So if we go from 1 to 2, yep, so we're putting electron density between the topmost oxygen and this middle carbon. And that electron density is coming from where? What have we changed in resonance structure number 2? Yeah, we're forming a double bond. And what have we lost in resonance structure number 2? What is a lone pair? So we're taking this lone pair and we are using this lone pair to form a double bond between the topmost oxygen and the middle carbon. So we show this via arrow pushing. We start our arrow from our source of electron density, from our lone pair, towards the location receiving the electron density, which is the bond between the topmost oxygen and our carbon. Does that make sense? Now, whenever you attempt to form a new bond, you have the potential to break a double or triple bond. So looking at structure 2, does it contain the double bond found in structure number 1? No. Does it have that double bond below? No, it does not, right? So as we form this initial double bond, the electrons found in this bottommost double bond are kicked out, and this double bond is broken. So in summary, our lone pair electrons are pushed down to form a new double bond, and our previous double bond is broken, leading to a lone pair on this bottommost carbon. Does that make sense to everyone, the logic behind arrow pushing? We're going to be doing a lot of practice on pushing arrows, and there's a book that I put in the library called Pushing Electrons that has a lot of practice in drawing resonance structures and utilizing arrow pushing notation. Now, so we have these 2 resonance structures for the enolate of acetone. In order to best represent our resonance hybrid, so if we were to draw our resonance hybrid from this, instead of drawing a formal double bond between these 2 carbons and between this carbon and oxygen, we instead use dashed line notation. So to give you a sense of how dashed line notation works, let's look at the following structure below. So as we notice here, instead of having a formal double bond between our 2 carbon atoms, we have drawn our bond as a dashed line. This dashed line across multiple atoms signifies that our electron density is spread among multiple atoms. The other major way that your books will showcase resonance delocalization of electron density, the fact that if we average out our resonance structures, our electron density is distributed among multiple atoms, is using a curved line. So for example, we have our skeleton of the acetone anion, and we draw a curved line between all of the atoms that are participating in resonance. So we draw this curved line, and then we signify the charge distributed among our 3 atoms. Now, why have we drawn a negative charge? Fundamentally, if we look at these top 2 pictures, what is being delocalized? What charge is being spread over multiple atoms? What charge do we see being spread over multiple atoms? Negative charge, exactly. So this lone pair worth of electrons is being distributed over these 3 atoms. So that's why we put a negative charge. Does that make sense to everyone? So let's look at another example, and let's try to understand how we portray resonance structures and how we portray resonance hybrids. So let's now take a look at resonance from the perspective of valence bond and MO theory. Let's try to get a sense of what orbital interactions are a signpost, are an indicator of resonance. So let's touch on our pi bonds. So pi bonds are the overlap of unhybridized p orbitals. So just keep that in the back of your mind. To have a pi bond, an unhybridized p orbital. Now, these two p orbitals are parallel and they overlap to form a pi bond. Technically, there should be phasing drawn here where you have regions of the same phase overlap. Now, an interesting feature of pi bonds is that if you have pi bonds adjacent to a parallel p orbital, these orbitals can then overlap and generate an extended pi bond known as a pi system. So let's draw an example of this. So suppose you're dealing with a conjugated alkene, such as that drawn here. If we're breaking this down from the perspective of MO theory, I'm going to draw the cis form just to make this interpretation a little bit easier on us. So if we're drawing this from the perspective of MO theory, I'm going to lay out each of my carbon skeletons, and I'm going to draw my p orbitals that are responsible for my pi bonds. Okay, so we have two pi bonds, so we have two sets of p orbital overlap. So here's our first pi bond, here is our second pi bond. Because these pi bonds are adjacent, we have adjacent parallel p orbitals, they can overlap and form an extended pi system. So instead of just sharing our electron density over a set of two carbon atoms, we can spread this electron density over 4 carbon atoms. So let's draw that out. Now, this is very beneficial from an energetic perspective because we are spreading out our electron density over a larger number of atoms. So our electron density is being spread over multiple atoms and multiple parallel p orbitals to form what's known as a pi system. Does that make sense to everyone? So whenever you see a p orbital adjacent to a pi bond, you can form a conjugated pi system. Okay, we have a special word to describe this delocalization of electron density, and we call this process conjugation. So conjugation is the overlap of p orbitals in 3 or more adjacent atoms to form a continuous pi system. And a pi system can be defined as any set of adjacent p orbitals or pi bonds. Okay, we've actually seen cases of pi systems before. Let's look at our good old friend ozone, as despite its simple structure, it holds a lot of interesting nuance. So if we take a look at ozone, O3, ozone, we've typically drawn it as one of 2 major resonance structures, depending on where you choose to place your double bond. In the first resonance structure, we have our negative charge on the right-hand oxygen. On our second resonance structure, we place our negative charge on the left-hand oxygen. What I really want us to focus on when we look at ozone is to look and see whether we have met the criteria for a pi system. So let's first identify, do we have a double bond? Do we have a double bond at play? Yes, so we have our double bond. We have our pi bond. Okay? Now, An interesting feature associated with pi systems is that you cannot just need an empty p orbital or a parallel p orbital. Another criteria to form a pi system is if you have an adjacent lone pair on an adjacent atom. So does everyone notice this lone pair on an atom adjacent to our pi bond? Now, in order to access a pi system, this lone pair, instead of being stored in a normal hybrid orbital, will instead prefer to be stored in an empty p orbital. So this lone pair is going to sit in an empty p orbital. So then, when we have our pi bond, adjacent to this pi bond, we have a lone pair that is sitting in a p orbital. And since we have a p orbital parallel to a pi bond, can we form a conjugated pi system? Yes. So this electron density in this p orbital will interact with the pi system or interact with our pi bond, and in turn, we end up with what is known as a pi system. So, a critical takeaway from this discussion is when you have a lone pair adjacent to a pi bond, that lone pair will end up in a p orbital, preferential. And your atom adjacent to this double bond will hybridize to place this lone pair into a p orbital. Okay, so to showcase how we draw out ozone using our curved notation, let's just do some practice here on curved arrow notation. If we want to go from the structure on the left to the structure on the right, what needs to happen? What needs to happen? So where do we need to form a double bond? On the left, right? So I'm going to kick my lone pair down, and I'm going to attempt to form a double bond. As I form this new double bond, what happens to my already existing double bond? It breaks, exactly. And we kick this double bond up to generate a lone pair. So this habit of arrow pushing to represent how we redistribute our electron density to get new resonance structures is a really critical skill that we'll develop, as this is how we're going to draw out the movement of electrons in chemical reactions. Now, if we wanted to give the most representative picture of ozone, if we wanted to give our most representative resonance hybrid picture, I'd probably draw ozone as looking like this, with a curved line between all three of my oxygen atoms, signifying that we have this double bond character spread over all three oxygen atoms. Does that, yes?
So in that case, instead of bringing down the charges, would it cancel?
So you'd still have a negative charge distributed throughout, but you'd also have a localized positive charge on the central oxygen. Yeah. Does that make sense to everyone? Let's now look at a few more examples of how resonance can start to impact hybridization. So, when we think a little bit about pi systems, when we overlap these pi bonds, when we overlap these p orbitals to form pi systems, we are generating what are known as molecular orbitals. So this is an orbital representing electron density distributed throughout our molecule. And we make molecular orbitals equal to the number of orbitals combined. In this case, our p orbitals that we've overlapped together. Now, for ozone, since we combined 3 separate p orbitals, we put 3 orbitals in, from MO theory, how many orbitals do we get out? 3. The amount in is equal to the amount of molecular orbitals that you get out. So we're generating 3 molecular orbitals. Now, this will be really important towards the end of this class, but let's now appreciate the fact that just like when we formed sigma bonds. Just like when we formed our bonding molecular orbital, every time we form a bonding molecular orbital, what other type of molecular orbital is generated? Bonding and its counterpart, anti-bonding, exactly. For each bonding MO we generate, an anti-bonding MO is made. There's one small subtle distinction that occurs when we have an odd number of orbitals. If you have an odd number of combined orbitals, a quote-unquote non-bonding orbital is generated, where the electrons are neither bonding nor anti-bonding. So let's get a sense of how this pans out with regards to phasing. And if there's one picture that I want you to keep in the back of your head for a later chapter, this is one of them. So since p orbitals are phased, a bonding orbital will involve an overlap where all the orbitals have the same phase. Does everyone notice in this bottom picture for our bonding orbital, all of the p orbitals have the same phase, right? Same color on each side, right? Now, when we deal with our non-bonding and anti-bonding orbitals, we're involving p orbitals of opposite phase. So we start to develop differences in phase across our molecule, and we call regions separating differences in phase a node. And the key thing to keep in mind is the number of nodes increases as you move up from bonding to non-bonding to anti-bonding. And that affects the properties and reactivity and accessibility of each of these types of orbitals. So to get a little bit of sense of what's going on here, what do we mean by non-bonding? So the best way to interpret non-bonding, what do we call non-bonding electrons? What's another word for non-bonding electrons? Lone pair, exactly right, exactly right. So when we think about non-bonding electrons, when we think about this idea that we have a non-bonding electron system, that is best represented by the idea of a localized lone pair. So for example, in this conjugated anion, this lone pair that is localized on a single atom would be best viewed as non-bonding. So this is a non-bonding lone pair. Okay. Now, another thing that I want you to appreciate in this diagram, if we compare your typical non-bonding interaction to this conjugated bonding orbital interaction, what molecular orbital is lower in energy? What's the lowest energy molecular orbital? If energy is arranged vertically, what's the lowest energy molecular orbital? Bonding, non-bonding, or anti-bonding? Bonding, right? So this overlap of p orbitals to form a conjugated system and form a conjugated bonding molecular orbital is stabilizing. It's a favorable event. Conjugation is stabilizing. So what we're going to do now is we're going to really focus on the brass tacks of how do we draw resonance structures? How do we push electrons to generate new resonance structures? And this is one skill that you're going to need to practice a lot at home. One of the books that I recommend that I've put on the library reserve is called Pushing Electrons. It's a wonderful tutorial on drawing resonance structures and has additional examples that I recommend that you review after class. So let's now talk a little bit about how do we draw resonance structures. So electrons in conjugated pi systems are delocalized. We've established that these electrons are spread out through all atoms involved in the pi system. As a general rule of thumb, when drawing resonance structures, you're going to avoid breaking a single bond. Why is this rule in place? Are sigma bonding electrons, are sigma bonds involved at all in conjugation? No, it's not called a sigma system, it's called a pi system, right? Additionally, make sure you never exceed the octet rule for second row elements. This is known as the n=2 rule. Now, we can move electrons shared in pi bonds to any atom participating in the pi bond. We show the movement of electrons using a curved arrow, starting from the lone pair or the source of electron density. So the arrow is describing the movement of electrons from one location to another. So for example, in this ylide, which is a common Wittig reagent used in organic reactions, we can push the electron density found in this double bond up to our carbon. Now this arrow pushing isn't just done willy-nilly. What's the logic behind why we chose to put our electrons on carbon? What's more electronegative? Carbon or phosphorus? Carbon. Remember, that was the exception that we discussed early on in this class. So we've, in effect, put a lone pair on the more electronegative atom. So even though this structure, does this structure obey the octet rule? Yeah, looks pretty good with regards to the octet rule, but are the formal charges reasonable? Does carbon like to have a negative formal charge? No. So if we had to pick one of these two structures to be our major, which structure do you think most reflects the actual distribution of electrons in our molecule? One on the left. So we'd call the structure on the left major, and the structure on the right minor. The reason being the structure on the left minimizes formal charge. The structure on the right, though, should not be neglected because it's a very good descriptor of how this molecule likes to react, where the negative charge is centered on our carbon. So the minor structure really provides us insight into reactivity and patterns of reactivity. And that's the point of drawing these structures. Now, as a general additional rule, it is preferable to place negative charges on more electronegative atoms and positive charges on less electronegative atoms. The reason why I review the carbon-phosphorus electronegativity value is because oftentimes students will think, well, phosphorus is more electronegative, when in reality, carbon is, and that reflects the reactivity of these reagents. So what I want us to do now is let's now take a look at the following structure, and let's try to draw a few valid resonance structures. Let's try to draw some reasonable resonance structures, and let's allow ourselves to break the octet rule. You can break the octet rule for resonance structures to make minor structures. So if I had to pick, where should I push this double bond's worth of electron density? To a carbon or nitrogen atom? What's more electronegative? Nitrogen. So I'm going to take my double bond and I'm going to put a curved arrow directed towards nitrogen. I'm going to put this structure in brackets, draw my double-headed arrow. Note it's not two arrows, it's one double-headed arrow. You don't want to indicate equilibrium on accident. And then we end up with the following resonance structure. This nitrogen now has a negative formal charge, and this carbon has a positive formal charge. So, is there another potential resonance structure we can draw? Can we push our electron density in another direction? Towards where? Towards carbon. Sure, that's perfectly valid. Let's showcase that. So we can push our lone pair. We can push our double bonding electrons towards carbon to make a lone pair. And that in turn generates the following resonance structure. This one has a negative charge on carbon and a positive charge on nitrogen. Are any of these two resonance structures that we've drawn very good? Do they fulfill the octet rule and do they have small formal charges? Do you think these are very major structures? No, not at all. These two structures are minor because they both violate the octet rule and they have terrible formal charges. If we had to pick, so if this is number 1, what would be the second most valid structure? If we had to pick from these two terrible structures, what would be the second most valid? Exactly, the top right, the structure with the negative charge on the nitrogen. Why? Nitrogen is more electronegative. So we're using similar logic to what we've used to assess Lewis structures to assess resonance structures. So what I want you now to do is I'm going to show you a structure, and I want you to draw a valid resonance structure for the following set of compounds. And try, if you draw multiple structures, to provide whether one's major or minor. So I'll check on you and we'll come to discuss in about 3 minutes. Everything going okay? Yep. And then here's our positive charge. Yep, exactly. Everything going okay? And just so always make sure when you move electron density from atoms in a pi system or a double bond, you can only push electron density to one of the 2 atoms involved in that bond. Oh, so looking at that structure, that is what's known as a polymer, because implicitly you change the number of hydrogens attached. So then try to think of ways, we have a double bond, let's try to move the electron density in the double bond to one of our 2 atoms. It makes this structure that way. Does that make sense? So that's what's known as a polymeric form. And do you notice how looking at this carbon has a different number of hydrogens attached? Yeah. So then when you're looking at drawing resonance structures, you can take the electron density in your pi bond or pi system and distribute it to one of the 2 atoms involved in that bond. So looking at this double bond, what 2 atoms are involved? The carbon and oxygen. Right. So then you can push your electron density to any one of those 2 atoms. If it's not involved in the pi bond or pi system, it can't participate in resonance. Does that make sense? Oh, just remember when you're drawing resonance structures, you can only redistribute electron density that's found in your pi bond to the atoms involved in that. So do you notice how this probably have formed a new double bond between an atom not involved in the pi system? Zeros look good, just make sure you're being very specific here. What 2 atoms are involved in that pi bond? Yep, the 2 carbons that are double bonded. So the electron density can only go to one of those 2 carbons. Yes. Yes, that's perfect. So to give everyone some guidance here, when you're drawing resonance structures, I want you just to focus on all atoms involved in the pi bond or pi system. So I'm going to highlight the 2 atoms involved in my double bond. So we have the carbon and this oxygen involved in my double bond. So when I'm drawing resonance structures, I can take the electron density in this double bond and distribute it to any of the atoms involved in that bond. So I can take my double bond electron density and push it up towards oxygen. That's one valid approach. And that would give me the following resonance structure. Notice how the electron density in our double bond can only be distributed towards the atoms involved in our pi bond or involved in our pi system. These 2 other carbons are not involved and do not participate in resonance. Another potential resonance structure you can draw, I first kick my electron density towards oxygen. Is there another way I can move my electron density? Towards carbon, sure. And to draw that alternative path, I'm going to erase this arrow and show the arrow going from our double bond to specifically the carbon atom involved in our double bond. And that in turn gives us the following resonance structure. So the oxygen now has a positive charge, the carbon has a lone pair and a negative charge. Does that make sense to everyone? Only focus on electrons involved in the pi system. Okay, with that established, let's now take a look at this second example. So we have a total of 2 carbons involved in this pi bond. Where would we want to push our electron density towards? To the left or to the right? Which one do you want us to start with? The left, okay? So let's do that. So let's push our electron density to the carbon on the left. Again, our arrow goes from our double bond to the receiving carbon. And let me make this really explicit here. Double bond to my receiving carbon. I'm going to draw curved arrows. I'm going to place the structure in brackets. And in this case, we have a positive charge on the rightmost carbon and a negative charge on the leftmost carbon. Does that make sense? This is actually the second most favored resonance structures for reasons that we'll talk about towards the end of chapter 4 and 5. Let's draw our second potential resonance structure. We can kick our electron density towards the carbon on the right, and that in turn would give us the following valid resonance structure. Of course, all the resonance structures I'm having you draw right now are pretty minor, right? Looking at all of the resonance structures that we've drawn, are they better than our original structures? No. They violate the octet rule. We have a ton of formal charges. But the reason why we look at these structures is to help see patterns of reactivity. And often the minor structure gives us most insight into how these molecules like to react. So we notice, for example, ketones have a fair amount of electron deficiency at this carbon. So they'll typically react with sources of electron density at this carbon. Yes?
So when you're asking when we like go through this arrangement?
So you won't often explicitly access a resonance form, but it just shows that our electron density in general is not distributed evenly between these 2 atoms, and instead, most of the electron density prefers to sit more on oxygen than carbon. We'll talk more about that later on. For now, let's just focus on the mechanics of arrow pushing. This is the most critical skill you'll need for the exam. Any questions on this? Let's just do more practice. Practice makes perfect for this. Okay, so another way that we can draw resonance forms is we can move electrons in p orbitals adjacent to pi bonds to form a new pi bond. As the new pi bond is formed, the initial pi bond is broken, and the electrons in that pi bond are moved to the atom not participating in the new pi bond. I know it's a lot of words, but the way that I like to think about it from a very tactile standpoint, the electrons in the lone pair are pushed down to form a double bond, and the electrons in the double bond are pushed up to give a lone pair. That's why we call this pushing electrons. This push and pull movement of electrons is how I like to think of drawing resonance structures. So to showcase this, we can take this lone pair on nitrogen and push it down to form a new double bond between carbon and nitrogen, right? When we form this new double bond, what happens to our original double bond? It gets broken, exactly. So our electron density in the double bond now gets kicked up towards oxygen. Why towards oxygen? Is oxygen participating in the new double bond? Looking, is oxygen participating in our new double bond? No. In general, your flow of electrons will go from a starting point, from your starting source of electrons, to an ending location where your electrons end up. Okay, always make sure your electrons are being pushed in a single direction. So as we notice as a result of this arrow pushing, we end up with a resonance structure for a very classic type of bond in biology, which is your amide bond. Looking at this resonance structure, is this resonance structure that bad? Looking at this resonance structure, does it fulfill the octet rule? Yeah. Are the formal charges that bad? No. So this is actually a relatively major contributor. Now, if you're really fixated on the MO theory interpretation and you really want to try to rationalize, well, why am I breaking a bond when I form a bond? Well, if you add electrons to a pi bond system, you're filling the anti-bonding MO, so you're breaking a bond. Any bond-making event typically coincides with a bond-breaking event. Does that make sense? Okay. Now, let's showcase a more complicated example. We can take this process of pushing electrons into pi bonds, and we can repeat this and distribute our electron density over multiple different atoms. So let's look at this heavily conjugated amine, and let's showcase how we can draw multiple different resonance structures. We'll do this one together. So first, I have a lone pair adjacent to a double bond. So can I kick my lone pair down to form a new double bond? Yes. So I'm going to take this lone pair, kick my lone pair down. When I form this new double bond, what happens to my existing double bond? It breaks, and the electrons get kicked up to the atom involved in that double bond. Okay, so let's draw that first resonance structure. Perfect. So everyone matching with me so far? Now, can we draw another resonance structure? Do we have a new lone pair adjacent to a double bond? Yep. So can we repeat this process? Yes. So let's change pen colors for that, just to showcase the second step of this process. So we're going to take our lone pair, we're going to kick it down to form a double bond. And now our previous double bond gets broken, and our lone pair electrons get kicked off to this carbon here. So let's now draw that resonance structure. Let's now draw that resonance structure. And now we have a lone pair on this tertiary carbon. Does that process make sense? Now, of course, we can draw some more absurd resonance structures than this, but let's only entertain the ones with 2 sets of formal charges. Let's not get hundreds of formal charges on our molecule, because those structures are so minor that they don't really contribute a significant amount. But of course, when we take the electrons in these double bonds and kick them up to form new lone pairs? We can, but they're so minor, they're not worth talking about. Only really focus on the relatively major structures, as those are the ones that you'll be interpreting to help assess reactivity and overall molecular bond length and strength. Now, a key takeaway from looking at this picture, if we think about the idea of the resonance hybrid as the weighted average of all of our resonance structures, if we look at this single bond is this single bond a true single bond in terms of its character? If we look at all these resonance structures, is that single bond a true 100% single bond?
No.
No. We see some double bond character in some of our resonance structures. So this single bond is typically stronger than a typical single bond. Typical carbon-carbon bond. Well, where this C, single line C, is representing a single bond. Does that make sense to everyone? So this, yes. Yes. So looking at all of the resonance structures, do you see structures in which there is a double bond between these two carbons? Yeah. So as a result of this small double bond character, our resonance hybrid puts a little bit of double bond character between those two carbons. So that bond is a little bit stronger than your typical single bond. Does that make sense? Perfect. So what I want you now to do is, given a conjugated system, this case is a conjugated enolate, which is actually it's a molecule very similar to that which I encountered in grad school. I want you to draw at least 2 valid resonance structures for this anionic species. Yes.
So you were saying on the
yes.
double bond right there, right?
Yes.
It's stronger than the single carbon.
Yes.
So that bond can go into the p orbital.
So yes, so if we think about the distribution of electron density, we can best draw it as the electron density is distributed among all of these atoms participating in resonance.
So that bond would just not be a sigma bond.
It's not. It's a sigma bond with some pi character.
All right. So
Yeah.
you could go into the
Yes,
All right.
exactly. So what I want you now to do is to try to draw 2 valid resonance structures for the following anionic species, and I'll check to see how everyone's going. And I would recommend starting from the source of electron density. Start from your lone pairs. Yep, good. But when it gets pushed down, what happens to that previous bone? Yep, exactly. Okay. You just push it up to the carbon atom. Yep. And so the lone pair ends up on that carbon atom now. Everything going okay? So then is that single bond? Is there any adjacent pi bond or any pi system between these 2 atoms? So that, but you can push your lone pair into a pi bond or a pi system. So you see an adjacent pi bond or pi system that we can look at. Yeah. So let's kick our lone pair on a double bond. This way? Yeah, exactly. And then when you form that new double bond, what happens to your existing double bond? Yes, exactly. Correct. So you end up with your anion on the carbon. Yep. Yeah. Okay. Everything going okay? Yep. That's one. Don't forget, there's a negative charge on this bottom left. So that is a valid resonance structure, but that's relatively minor compared to.
So all right.
But that is correct. That is correct. So. Everything going okay? Yep, looks good. Oh, remember that the anion is still present.
Oh, I just forgot to write this.
Yep. So that is a valid structure. That's a valid structure. Yep, perfectly fine. There's one more actually you can think of as well.
Okay.
Yes. Sure. So try to focus on drawing one movement of electrons at a time. Because this logic is fine. It's more if you do it all at once. In general, for resonance structures, you draw one moving electrons at a time. Just so that way it's easier to. Yes, because this carbon has 5 bonds. Yes. So looking at this method, is there a pi system or a double bond? So you can only push electrons in resonance with conjugated pi system or one pair of adjacent double bonds. So this arrow push, your double bond up to the oxygen is fine, but this one is not. In general, you want to draw one movement of electrons per resonance structure. Because when you start drawing multiple arrows going in different directions, it's better to break it into separate steps. Everything going on? Yep, that looks good. The first one looks good. Yep, that looks fine. All good? Yep, looks fine. Oh, but don't forget the lone pairs. And so So let's come together to discuss. I saw a lot of reasonable responses, but again, I always have to emphasize, you can move electrons through conjugated pi systems. So we have our lone pair here, and I see a double bond. So I'm going to take my lone pair, and I'm going to push the electrons down to form a new double bond. And what happens to my existing double bond? It breaks, exactly. So that in turn generates our first resonance structure. And it's interesting that everyone is already picking up on a very interesting potential resonance form in this molecule. Now that we have the lone pair on this carbon, we have 2 potential adjacent double bonds to work with, right? We have both the ketone and the ester double bond to work with. I'm going to draw the next most favorable resonance structure, and I want us all to think a little bit on why is this structure so favorable. So I'm going to take my lone pair and kick it down to form a new double bond, and then our double bond that we currently have gets broken. And that gives us our second major resonance structure that I'm going to draw in a slightly different color. I'm just going to zoom out so that way there's a little bit more space here. Here is our second major resonance structure. There are multiple valid answers for this question. Would anyone like to comment potentially on why especially this third structure is highly favorable? Why is it? Yes. So try to think about the location of the lone pair. Where is our negative charge located? Oxygen, right? And is oxygen more electronegative than carbon? Yes. So the reason why structure number 3 is relatively major has to do with the fact that it places our negative charge on the most electronegative atom. Does that make sense to everyone? Yes.
So if you were to have done the same thing you just did, but on the other oxygen double
Yes.
bond, it's equally as.
It's a little bit less, but it's also reasonable. So in terms of our criteria, there are many reasonable structures. And once you draw all of them out, then we can analyze and assess which ones are most favorable. And that's what we'll be doing later on in this chapter. Does that make sense? Perfect. Okay, so now that we're comfortable drawing resonance structures, let's now add another rule. So if there is an atom with an empty parallel p orbital adjacent to a pi bond, the electron in the original pi bond can be pushed to form a new bond by breaking our original pi bond. So this is best shown using arrow pushing notation. I have a cation on my leftmost carbon, right? So this cation has an empty p orbital. So this whole system is conjugated. I'm going to push my double bond electron density to form a new double bond between my adjacent carbon atoms. Does that make sense? That gives us a new double bond, and our cation has now been moved to the rightmost carbon. This is one resonance form that you'll encounter quite often. Now, just like we did with the lone pairs, we can repeat this process and draw multiple resonance structures for highly conjugated systems. So we have a cation on our leftmost carbon, just like before. Can we push our double bond electron density to that cation? Can we form a new double bond? Yep. So let's showcase that. I draw my arrows going from my double bond to between my carbon atoms. The reason why it's between, I'm forming a new double bond. So then let's draw using my double-headed arrow. We now have a cation on this carbon, and this allylic cation, or this cation adjacent to a double bond, can participate and engage in further resonance delocalization, right? Is this cation now adjacent to another double bond? Yep. So let's take this double bond electron density and let's push this electron density towards my cation. So I'm going to form a new double bond, and as a result of forming this new double bond, I generate a new cation. So let's showcase that. Oops, that's a little ugly. Let me fix that to make it more aesthetically pleasing. Here we go. So here's our third potential resonance structure. Now, in general, when you think about cations, you want the cation to be on the carbon attached to the most other carbons. We'll talk about the reasoning behind this rule later on. For now, just from the knowledge that we have currently, we'd say all of these structures are equally valid. With a little bit more nuance, this third structure drawn is probably the major structure for this list of resonance structures. Is everyone comfortable drawing resonance structures when you have a cation system? Yes.
So the carbon that has a positive charge,
Yes.
it doesn't have hydrogen attached to it.
It does not. It only has 3 carbons attached. Exactly right.
Can you elaborate just a little bit? Because when I see that first example, all I can see is that very, very first example that we did when we numbered each carbon, where it kind of looks like you're saying, oh, that doesn't count, like because it just
Let me provide carbon labels to help you see. So 1, 1, 2, 3, 1, 2, 3. Do you notice how the carbon has shifted between carbons 2 and 3 to now it's between carbons 1 and 2? So our actual distribution of electron density in terms of where the double bond is located has changed. Does that make sense? Mm-hmm. Perfect. Okay, now what I want you now to do is to take a look at the following molecule, and I want you to draw a valid resonance structure for this molecule. And if you can draw multiple, that's even better. Everything going okay? Everything going okay? Any questions? In terms to the formula, the double bond gets pushed. The laser gets pushed. The double bond electron density gets pushed to between. That's what it is. Yeah, that's fine. That's fine. Yeah, the cation will be there. Yeah, that. Everything is all okay. Yep, it's good. The only thing is the cation. So if we move the double bond in between these two atoms, what carbon atom now has less than 4 bonds? Which carbon atom no longer has a double bond? Yes. Yep. Exactly. Yep. Looks good. The arrow pushing looks good. So I see a lot of reasonable solutions so far. So let's now talk about this example. So I have a cation adjacent to a pi bond. So I'm going to kick my electron density found in my double bond down. And just to make sure we're 100% clear, the double bond electron density gets moved to between the carbon atoms. So your arrow should go between the carbon atoms. I know it seems nitpicky, but it's really important that you follow these formalisms. So we have our first resonance structure now. That looks something like this. Let me fix that. And our cation ends up on the carbon that no longer has a double bond. We can draw one more resonance structure because we now have a cation adjacent to a pi bond or a pi system. So we're going to kick our double bond down and we're going to form a new double bond, and that results in generating a new cation. So that in turn generates the following resonance structure. And if I had to pick one to be the best resonance structure, the structure in the middle would be the preferred resonance structure, as the cation is on a carbon attached to the most other carbons. We'll talk about this rule later on in the class. Any questions on drawing resonance structures for cationic systems? Okay. What we're now going to do is we're going to combine this idea and we're going to develop our last major rule for arrow pushing. If a lone pair is adjacent to an atom with an empty p orbital, or an atom that can form additional pi bonds, the lone pair can be used to form a pi bond. So for example, we have a cation adjacent to a lone pair, right? What a cation implies, we have an empty what? P orbital, exactly. It's sp2 hybridized, it has an empty p orbital. So we can take this lone pair adjacent to our p orbital and form a pi bond between our atoms. In this case, we push our lone pair electrons between our two atoms to form a new double bond. Now, to showcase how this works fully, we can combine all of our rules together and write very complicated resonance structures. So in this case, I'm going to use my first set of rules in that I have a cation adjacent to a double bond. So can I push my double bond down to form a new double bond? Yes. So I'm going to take this double bond, I'm going to push it down to form a new double bond and a new cation. So we can generate our first resonance structure, which looks a little bit like this. Okay, so we have our first resonance structure drawn. And now, because we now have a lone pair adjacent to a cation, can we push our lone pair down and form a new double bond? Yes. So let's do just that. We take our lone pair and we push it down between our two atoms to form a new double bond. Does that make sense? Okay, just like we did up here, right? We have a lone pair and a cation. We can form a double bond. And that in turn gives us the following resonance structure. And if we had to pick which structure was the most major, which structure from the ones drawn follows the octet rule most stringently? The last one, right? So we'd expect this structure to be preferred. Does that make sense to everyone? What I want you now to do is to apply these ideas to a new example. So I want you to draw at least 2 valid resonance structures for the following compound. And this is a very fun system to talk about because this question actually gets way harder the more information you know. But for now, we'll just follow our rules for resonance structures and draw 2 valid resonance structures. Everything going okay? Yep, that looks good. Mm-hmm. Everything going okay? Yep, that looks good. Yep, that looks good. Yep, looks good. Yep, looks good. Any questions? Yep, that looks good. Yep, looks good. Any questions? Yep, that looks good. Any questions? Yep, looks good. So, compiled among the class, we have at least 6 different resonance structures. Let's just focus on the first few. So one of the most common things that I saw looking at everyone's paper is they saw a cation, they saw a double bond, and they pushed the lone pair, they pushed the double bond electrons to form a new double bond and a new cation. Perfectly fine, perfectly standard. And that in turn generates the following structure. And 7-membered rings are always so awkward to draw because as chemists, we're so used to drawing 6-membered rings. We don't even have the benefit of the 8-membered ring, which looks like a stop sign. Okay, nonetheless, we have the following resonance structure. Let me just clean up this double bond so it's clear that what atoms it's between. Okay. Now, from this perspective, we now have a new cation adjacent to another double bond.
Is there a reason why you put the bond outside the?
No reason whatsoever. We can even draw it on the inner region. Both are fine. So now that we have a new cation and a new double bond, we can also push our electron density to form a new double bond and another new cation. And that in turn gives us the following structure. Of course, the reason why I'm drawing these resonance structures first is there's another very obvious resonance structure that many people in the class have drawn. We see a cation, and what's adjacent to this cation? Two lone pairs. So we can also form a double bond using that resonance method. So we're going to kick our lone pair down, and we're going to form a double bond. Now, this structure on its own is reasonable given the information provided. In reality, this structure is not particularly favorable for reasons that we'll discuss towards the end of this class, actually. The beautiful thing about organic chemistry, in my opinion, is that the more information you have, the more capable you are to assess complex problems, and the more very odd behavior of molecules and very odd structural preferences for molecules become apparent. So, any questions on drawing these resonance structures? Everyone comfortable? I really encourage you to break open your book and practice these, because this is something that you're going to need to have down, because when we get to reaction mechanisms, if you don't have arrow pushing down, it's going to be very confusing. Let's now just wrap up this system with one last discussion. So there's a special type of conjugated system that we call an aromatic system. So an aromatic system is best defined as a set of conjugated pi bonds in a ring. Conjugated pi bonds in a ring are aromatic or anti-aromatic, depending on the number of electrons systems. The most common aromatic system that we see is the benzene ring or phenyl group. Now, there are many resonance structures we can draw for these aromatic systems, but the most common is pushing our pi bonds in a clockwise or counterclockwise direction to generate a new set of pi bonds. Now, in reality, in this conjugated system, is our electron density in these double bonds distributed about all of our carbon atoms in this conjugated system? Yes. So the most common way that many people will draw a benzene ring is a six-membered ring with a circle in the middle. So this is an aryl, and more specifically a phenyl group. Whenever you have lone pairs or any potential opportunities to conjugate with an aryl ring or an aromatic system, that's a very stabilizing event. The reason being, in an aromatic system, we have delocalized our electrons over 6 carbons. So it's a highly conjugated system. There are additional reasons that we'll get into later on in this class, but aromatic systems are even more stable than your typical conjugated system due to their unique arrangement of pi bonds. Now, to wrap up this portion of the chapter, what I want you to do is to draw a valid resonance structure for the following molecule, which is known as cyclooctatetrene. It looks like a stop sign, but try to draw at least one valid resonance structure. Yep. Yeah, exactly. Yep, exactly. When you're pushing your double bond, try to move all of your double bonds in a counterclockwise direction.
So now we do
And it's only in this case because instead of having localized charges, you're able to redistribute double bonds to all of your atoms. And this is a special case for aromatic systems, where you have your double bonds conjugated and in a ring. Exactly. So to showcase the major resonance structure, we're going to, as it is a typical, in this case, it's an anti-aromatic system, we push each of our double bonds in a clockwise direction, and that generates the following resonance structure. In terms of definitions, we best define an aromatic system as having 2n plus 2 electrons. So, for example, 6 electrons, 2 electrons. And we call an anti-aromatic system as a system containing 2n electrons. Oops. Well, 2 electrons aren't seen since by definition you need more than 2. So 6 electrons, 10 electrons. While anti-aromatic follows the 2n form, so 4 electrons and 8 electrons. And as we'll discuss in a later chapter, I want to introduce you to this idea of aromatic and anti-aromatic, because aromatic systems are quite stable, while anti-aromatic are characteristically unstable. And we'll delve more into this in later chapters. With that, that's all I have slated for today. We'll do more practice in combining resonance structures to generate resonance hybrids, and then we'll move on to acid-base chemistry. Just as an announcement, we're pushing the scheduled exam back a week. I'll announce the exact exam day next week, but it will not be next week.